episode 53. 'Tis the season, ality. And welcome back for another edition of the Syzygy podcast. My name's Chris Stewart. Sitting opposite me at the table in her office, Dr. Emily Brunsden.
Hello, hello.
So we had a really nice time last week, didn't we?
It was so fun, yeah.
At the Podcast Social Club. If you're joining us for the very first time because you were at the Podcast Social Club and you came along to see us up there in Thirsk, then hello, welcome.
Hello.
Nice to have you on board. And if you didn't manage to make it along to the lovely city of Thirsk, is it a city? Does it have a... Okay, here in the UK...
It's a market town, right?
It is... Well, it's definitely a market town because it has a very large market square. But I do know that in this country, things like, conurbations of buildings have different statuses depending on whether or not they have large buildings with steeples on top that have people in funny hats inside. Like if you've got a cathedral, then you're a city or something.
Isn't it based around a number of pubs as well?
Well, probably. But, I mean, that would make York the centre of the universe then, because York has a pub on every corner. But I don't know. Anyway, Thirsk, thank you so much for coming along the Podcast Social Club. We had such a great time. And the fact that when we asked, is there anyone in the room who's listened to us before, and not a single hand went up, to me, that just means we've got a lot of potential to reach a bunch of new people. So welcome on board. It was great fun.
Yeah, and thank you all for voting for me as well. That was great.
Yeah, I have gotten over the fact that it's now 2-0 to Emily in the Great Syzygy Space Off Stakes. Look, all I'm saying is just wait till next year, right? I was robbed, and next time we do a GSSO, I'm coming in hard. I'm taking no prisoners, right? Gloves are off next time.
No, okay? You better start your training now, Chris.
Mate, I'm on it. I am all over the next one. You just wait and see. Anyway, that's enough of that. Listen, we've got a very special episode today because we were contacted a little while ago by one of our brand new Patreons. I think we gave him a shout out a couple of episodes ago, actually, Keith Mazzullo, who got in touch with us and said, look, I love what you do, which was really nice. Thank you very much, Keith. But also said, I'd be really fascinated to hear a little bit more about this thing that I've just been reading about in the research, very recent research paper, which was all about how could we detect whether or not a planet around a different star, an exoplanet, whether or not it could have life on it. And there are a number of different ways that you could do this. But this was a really interesting one. This was all about, could you detect seasons on that planet? Could you find a signature of seasonality? Summer, winter, autumn, spring, or whatever they might call them on that particular place. Could we detect that? And that's a really interesting idea. And Emily, you went and had a look into this. It is an interesting idea, isn't it?
It is very interesting, yeah. So the topic of biosignatures generally, so biosignatures are the things that we can detect that would tell us that there's life on a particular planet,
right.
Whether it's an exoplanet, one of the moons in our solar system, or even Mars, for example.
And generally that's when you say biosignatures, you're talking about what, chemistry?
Well, something that is going to tell you undoubtedly that there is life.
But what's the range of possible things? I mean, yes, okay, I guess you could see, if you look hard enough, you could see cars driving around and vapor trails across the sky from the planes and things. But we're not talking about that. Are we talking about detecting chemical signals? Are we talking about detecting, possible other kinds of signals? What's the range of possible things that we could see?
Yeah, so there's about 10 different things that we look for, right?
Yeah.
Well, 10 different types of biosignatures, if you like. Now, if we dial this back a little bit and go into kind of what conditions we are really looking for when we're looking for, say, life, we're basing most of this knowledge on the life that we have here on Earth, right? So there's three kind of core principles that we believe that any life that at least is going to be easy to find is going to require. So the first one is some kind of chemical or thermodynamic disequilibrium. So what that means is something's out of balance.
Right.
And you need something to be out of balance because otherwise you can't, most of the detection methods require something to be a little bit out of balance.
And the notion of something being out of balance, why would something out of balance be a signature potentially for life?
So one example is for the Earth. Mm-hmm. We have lots of methane in our atmosphere. Now methane, we also have lots of oxygen. So methane reacts very readily with oxygen to form carbon dioxide and water.
Sure.
So if you're going to have lots of methane in its natural form, if you like, then there must be some source that's providing that methane.
Something's got to be making that.
Otherwise, it would have all changed to these other oxidation products.
Right.
So we know that there are things on Earth that produce methane. And the most efficient source of methane is life.
Okay, so we're looking for signatures of stuff happening on the planet that, as you say, is out of balance. It's out of whack. And the implication of that is that something's causing that, and that something may well be life.
Yeah.
Okay.
So number 1 is this disequilibrium.
Yep.
Number 2 is liquid water.
Mm-hmm.
So we don't understand any form of life on Earth that doesn't have some kind of process that involves liquid water at some point.
Okay. So it's not the smoking gun of life, but it's a really, really good indicator based on what we know of all the life we've found in the universe so far, which is us.
And the third one is an energy source.
Uh-huh.
So that's for the Earth. The majority of life uses the sun directly as an energy source, whether through photosynthesis for plants or eating things that photosynthesized for other things.
Yeah, you follow it down far enough and it's all basically the sun. Except, aren't there some life forms on Earth that are getting their energy from underground?
Yeah, so there are a few that, for example, live around these fumaroles, these underground hydrothermal vents. They're extracting energy from the geothermal energy of the Earth.
Which is also really interesting, isn't it? Because
it's really cool.
It's a really nice example of, but it doesn't have to be from the sun.
No.
It can just be energy and it'll work.
Exactly. There's also some examples of types of life that live off chemical reactions underground.
Right.
So they can basically use chemical processes to produce energy.
Yeah.
So you need an energy source.
Yeah.
And this is why we haven't given up on places in the outer solar system like the moons of Jupiter or Saturn, because they can have energy sources that are different to the ones on Earth.
Yeah, there are a couple of moons, aren't there? You can remind me what they are, which are quite active. Quite volcanic and sort of energetic.
Yeah, so our 3 favourite ones are Titan around Saturn, and that's probably got some geothermal processes. It's definitely got a lot of atmosphere and things going on. We also quite like Enceladus and Europa. So Enceladus is around Saturn, Europa is around Jupiter, but they're quite similar actually themselves, both big icy balls, but because of gravitational tugs with their planet, they are probably got very large liquid water oceans underneath those icy caps.
And a very long way away from the sun. So, if it did turn out that there was life on any of those, then that life is getting its energy from the moon, not from this very distant, tiny sun in the sky. I mean, we get a lot of confidence, or maybe not confidence, a lot of hope from the fact that we do find, like pretty much anywhere where you could find life on Earth, you do. And the fact that you do find these chemical, the ones who are getting the energy from the chemical reactions, the ones who are getting the energy from the undersea vents, it gives us a lot of hope. What we don't know is whether or not all of those different kinds of life forms are actually all coming from one original event, which was, the origins of life on Earth, in which case they've all just spread off and invaded any niche that they could find. And without that event, there wouldn't be any. Or is it that you just get life where there's possibility for it? And interesting, very interesting question.
Yeah.
Don't have time to get into that today. Moving on.
So the 10 types of biosignatures we have, I've sort of grouped them into 4 broad categories. There's kind of, we'll start with the least likely, shall we? So and this has only got one type in it, which is technology. Mm-hmm. So if we saw alien technology, that would be a biosignature.
That would be the smoking gun, quite literally. If you saw a smoking gun, then you're not going to get that naturally.
Yeah, you might not see it for very long if those aliens are pointing guns at you.
Exactly. Well, at least we know. Boom.
Yeah.
Oh, well.
So that counts, but that's not really a serious search that we're doing, apart from the programs like SETI, which are more looking at communication methods.
Yeah. Yeah, and just to be clear, that would be quite amazing. That would be
definitely, yeah.
That would be search for a very specific, narrow band of life, which is intelligent, technological life, of which the vast majority of life in the whole range of life is not. Mm-hmm. So there are other ways. So that's number 1.
Yeah. The next group out of 4 I've got is these microscopic or macroscopic physical structures.
Okay.
So these are kind of things that have been made by life that we have actually physically found. So an example would be a fossil.
Right. Okay. Yeah. So we're not talking buildings and cars and planes. We're talking no. This is a life form that we found encrusted in a rock.
Yeah.
From very
and
long ago.
there's other types, but basically, can we physically find something?
Yeah.
So that would happen, for example, if Curiosity, the rover on Mars, found something physical to suggest that life was there.
Wasn't there a number of years ago rock samples found on Mars, or was it on the moon? I don't remember. Which had tiny little traces in them that looked like they could have been the burrowings from minuscule bacteria or something like that.
There was a meteorite that we have found on Earth that we split open.
Yeah.
It was a meteorite from Mars, if I recall. And it looked like you had these kind of fossilized bacteria kind of structures. That hit the news in a big way at the time. But since then, there's been lots of explanations that are non-biological for these.
It got very, very noisy in the headlines and then went away, which is always a sign that, well, or not.
Yeah.
It might not be that. In fact, there's a lot of reasons why it probably isn't.
So probably not that one.
Yeah. But that kind of thing. If you can find fossils, if you can find, definitive traces of, well, that was made by something alive, or was itself something alive at some point.
Yeah. Okay, so there's those, and we're really only going to find those from either things that have come to Earth or us going out and getting them, which is limited to the very nearby
fairly
solar
limited
system.
range of sources there.
So the big category that has quite a few different ones is probably more what you think of when you think of biosignatures. So these are things that we could see on an exoplanet, for example, different types of reactions. You have isotopes, so particular ratios of different types of the same chemical that could only occur with life. And methane is an example. There is different ways you can create methane. Biological sources create methane in a slightly different way to geological processes.
Right.
Chemicals themselves, so can you see the methane, for example? Organic molecules, minerals, and atmospheric gases and atmospheric pigments. So this would be as the overall color of your exoplanet, kind of bluey green, which might suggest you've got a biosphere or something like that.
I guess there are limited ways of getting different colors on a planet, and certainly if you look at the Earth, then we know that its bluey greenness is coming from the water and the landscape. And green doesn't come up a hell of a lot in rocky worlds. Like, you don't see a lot of green on Mars, for example. You don't see a lot of green on Venus. See a lot of green on Earth for a very important reason. Yeah. Yeah, okay.
So those are the kind of the group ones that we're generally looking for when we talk about atmospheric biosignatures and exoplanets. And then there's this kind of fourth category, which is what we're going to talk about today, which is this kind of just temporal variability. So most of those other signatures, you measure one thing and you've got it, right? You measure that there's an alien spacecraft there, or you measure that you've got a particular isotope ratio of methane, then that's your measurement and you know that there's life.
Yeah, and it doesn't matter if you do that today or in a week or in a month, you've made that measurement.
Yeah. So temporal variability means that something's going to change over time that suggests there's a cyclic biological process that's happening. And one example the example we're looking at today is seasons. Now, seasons themselves, of course, not caused by life.
No, there aren't seasons because we're here. That doesn't work that way.
No.
Seasons come from some other astronomical.
Well, indeed, yeah. So they come from the Earth's tilt. So the Earth in its orbit around the sun is tilted over by 23.5 degrees. Mm-hmm. And that means that you've got one hemisphere that's getting proportionally more sunlight at any one time. So that's getting summer. And then as the Earth orbits around the sun, the other hemisphere gets, again, proportionally more sunlight.
And not due to the idea that at some times of the year the Earth is closer to the sun than at others, which is a common misconception.
No, we're actually coming into nearly the point where the Earth is closest to the sun, which is around January time. So for the Northern Hemisphere people, it's very, very clear that we don't have summer in January because we're closest to the sun then.
Yeah, and it's pretty cold outside.
It's pretty cold,
That's not that. So it's due to the tilt of the Earth. That's where the seasons come from. Okay. But how does that then turn into a biological signature, right? That's an astronomical fact about the Earth. It has seasons.
Yeah. So what the seasons do is they change a parameter called insolation. And insolation is just a fancy way of saying amount of sunlight that's hitting a place.
Not insulation, but insolation.
Yeah.
Sol as in sun.
Indeed.
So coming in, hitting, bouncing off. How much sunlight is falling on the planet?
Yeah. So you can even think about how many photons are you getting to hit a particular square meter.
Right. Yes. And so if you're tilted, as we are in the northern hemisphere at the moment, you're tilted, which means the sun's coming in at a lower angle, which is why the sun's lower in the sky all the time, which means any particular bit of land is only getting glancing rays. You're getting much less sunlight per square foot. That's the insolation.
Yeah.
Whereas down in the southern hemisphere, very hot and sunny because the sun's coming directly down on top of you and you're getting lots of sunlight per square meter. Yep.
So insolation changes over the course of a year, and it turns out that life responds to that.
Yes, well, we do know that,
in
don't
a
we?
very
Because,
obvious way. Yeah. I mean, we can look outside right now and see trees that are very, very bare because it's coming into the middle of winter, and they've lost all their chlorophyll. Then they've died. The leaves have died off, and so the whole surface of the planet's kind of changed color a little bit.
So, if you were looking at a distant planet and it changed its signature, whatever you're looking at, on a seasonal basis. This time of year it's like this, and then 6 of its months later it's like this, then that suggests something's reacting to those seasons. Right?
Yeah.
Everything's going to have seasons of some kind if it's got a little bit of tilt, but the reaction to that, the changes due to that, are potentially biological.
Exactly. So there's two kind of ways we can look at this. We can look at actually overall surface color, if you like, or at least you got to remember this is the surface that's pointing towards us.
Yeah.
So we'd have to measure this at times when you've got this kind of summer, in quotation marks, hemisphere pointed towards you from this exoplanet, and measure at times when the winter hemisphere is pointed towards you. And we'll see a color difference based on the different, well, you would on the Earth, let's say, based on the fact that you've got lots of green life in the summer, much, much less in the winter. But you can also do this with changes in other biosignatures as well, and with a seasonal variation. So you can do this with chemicals in the atmosphere.
Right.
And these are based on real measurements on the Earth that do change. If we measure the measurements of carbon dioxide and methane over time, then we do see a seasonal variation whereby when you have lots of photosynthesis, then you're producing much less carbon dioxide because you've got that opposite reaction happening.
Because that's what the chlorophyll does.
Yeah.
It takes the carbon dioxide and makes oxygen.
Yeah.
And so when you've got lots of green things, then you're turning lots of this into lots of that. And if you don't have as much green stuff, then much less of that reaction is going on. And you'd see a different signature of that in the atmosphere.
Exactly.
That's clever.
Yeah, and methane has a similar cycle.
Yeah.
So when we've been able to make these measurements based here on Earth by looking at the seasonal variation of particular field stations with their measurements of carbon dioxide and methane.
Cool. So this is hypothetical at this point?
Yeah, so coming to the paper, it's a really nice paper.
Yeah, we should probably talk about who are we talking about?
Yeah, so this is Olsen et al., who looked at, basically, it's kind of like a mixture of a thought experiment and a feasibility case study.
Mm-hmm. Where have they published this?
So this came in May 2018 in as Astronomical Journal Letters. And it's different to the normal kind of papers that I read. I'll be honest. So normally when I'm reading papers in my area, I'm looking at either there's a new theoretical technique that's been developed, or and there's lots of maths and lovely equations,
yep.
Or there's a new set of data that's come from a telescope and that they're trying to explain, things along these lines, or there's a new physics that they're trying to say, well, maybe this type of physics is happening in this environment. This paper is a bit more, it's kind of speculative, but not in a non-scientific way. So it's speculative about could we see these things, but it then tries to qualitatively make that judgment using real data.
Right.
So, for example, there's a lot of data on these cycles from the Earth and sort of looking at, well, what are the actual changes based on life on Earth? Are they detectable within our current limits of detectability? That kind of thing. So there's quite a lot of astro content in there as well, looking at things like orbits, looking at axial tilts of planets. But there's also quite a lot of biology in there as well, looking at what sort of chemical species. So that, for example, they take 3 chemical species and say which would be the best to do this kind of analysis for. And the conclusion comes to oxygen is probably the best one to look for. So
based on abundance and relevance to how that will change with the seasons and with life. Yeah. Okay.
And there's quite, it's very honest. It sort of talks a lot about what understanding is missing from these things. So, for example, if you think about we're doing some spectroscopy to figure out what chemical elements are present, then there's a lot of things you've got to consider. It's not just there's oxygen there. That's great, but you've got to think about the impact that the star has, what type of star this particular planet goes around would change it, what the actual construction of the planet's like what is the planet made of, basically, to begin with, because that then impacts the geology of the planet. And indeed what the biology is, because most of the assumptions that we're making are based on Earth. And
is there, how much of the speculation is based on Earth now? Earth is in a very strange period in its evolution, in the evolution of life on Earth. We're in a pretty weird and non-normal period right now, in that the Earth is covered with these strange bipedal hairless apes who are doing all sorts of crazy stuff, and that's not normal for Earth. We're quite abnormal for life on Earth right now. You wouldn't want to base all your decisions on, well, let's go and look for something that looks like Earth 2019.
No, and indeed what you want to do is maximize your chances. So if you think of Earth and the time that life's been on Earth, then for the vast majority of that time, it's been very microbial or gloopy stuff, right?
Yeah.
I can tell I'm not a biologist at this point.
No, those are actual terms. That works.
So no, it is. The paper acknowledges that. So they do look at the early atmosphere of the Earth. And they do also talk about maybe you couldn't really detect the oxygen change from life until something like 2 million years into the development of life on a planet. So, there's kind of that acknowledgement that whilst we're looking for something that's like Earth, it might not be at the same stage.
But then again, life has been on Earth for, a couple of billion years, I think, is the estimate.
Yeah.
And so, having to wait a little while is not too bad, because there's still quite a long span of life on Earth that you could potentially go for. But I guess what you're saying is it's important to look back to what is more representative of the history of life on Earth, which is not humans.
Yeah.
It's not dinosaurs. It's goop and bacteria and, large amounts of water swarming with very small things.
Yeah, and we've had photosynthesis happening on the Earth for a very, very long time. Yeah. So that seems like a good place to kind of start. Yeah, so it does talk a lot about this, and it talks about other challenges like what if the obliquity of the orbit is quite different? So
obliquity.
So this is the angle that we're seeing it at.
Oh, I see. Right. Yep. Not the angle that it's going around, but the angle we see it.
Yeah. Yep. Well, actually, the eccentricity, which is how circular the orbit is, or if it's an oval shape, or if it's a crazy kind of comet.
Right, yeah. Does it swing close to the star and then go really far away?
That would really change things
mess
quite
things
significantly. Yeah. And there's quite a lot of talk about different distributions of continents. So if you had all the continents in the northern hemisphere, for example, would that change your measurements to if all the continents were in the southern hemisphere? Because most of the photosynthesis is assumed to happen on the continents.
So, they're even going so far as to say, let's assume we have continents.
Yeah.
Let's assume we have... if we're talking about, let's look for watery places, then, you can probably make some assumptions. But I don't know. Is that a thing? Continents, I guess, are a normal thing on a planet thing. The crust is made up of bits that shift around. I don't know.
Well, we've only really got one example of them, but...
But do other planets, I know that we've got continents separated by oceans, but actually what you're talking about is large bits of crust fitting together like the bones of our skull, but sliding around each other and sliding under each other. Do we see that elsewhere?
So Venus has had a bit, most other planets don't have huge amounts of geological activity in a solar system, purely because they're too small, so they've kind of cooled down enough that any liquid magma, for example, is very, very deep.
Right,
so
of course.
We don't get that
our
anymore.
Continental movement is fueled by all the stuff that's going down under the surface. And if the whole planet cools down, then that fuses together, like the bones of the skull. When a baby's born, those bones are still all moving around, and there's bloody great holes in them, turns out. But as a as a kid gets older, those bones fuse together, and that's what's happened on Mars.
Yeah, well, Mars probably didn't even have time to build up a really continent. It cooled very quickly. Venus has got some geothermal sort of continent style stuff, but that's about it, really. So I mean, the assumption's just is it an Earth-like thing? So, well, and maybe that's an okay assumption, because if you're going to assume, well, you're going to look out and see thousands of exoplanets, maybe you just pick the ones that's most like Earth and hope that the conditions are similar.
It makes sense, right? You look where the light is, you go and sit, and if you, as you say, there are thousands of exoplanets now. I don't know how many of those would fit into the category of, well, let's look at those. It might be hundreds, it might be 2, I don't know. But that's presumably where you start. You look where it would make the most sense.
Yeah. So coming back to biosignatures and where this kind of fits in, biosignatures turn out to be a lot harder than I kind of naively thought they were. And I might have said this before, but I'm not a very prolific chemist or biologist, but I sort of thought, if you get a bit of methane, then, you can say that there's life there. And that's easy, yeah.
Right, yeah.
Turns out it's actually not easy at all. It's really tricky. And there's huge problems with any kind of thing, any biosignature where there are false positives. So these are things that mimic the biosignature but are actually not biological.
So you mean you find evidence for, say, methane, and it's there, but that doesn't mean it's biological? Is that what you mean?
Yeah. So it means it's come from an abiotic process, like geothermal process, for example.
Because it turns out that chemistry and atmospheres and planets are complicated.
Yeah. I mean, we talked about all the way back in episode 9 about Mars having seasonal variance in some methane measurements.
That's right, we did. Yes.
That Curiosity measured. And these are highly controversial measurements. I went back and had a look at kind of where that research is sitting today, and it's all kind of up in the air. Nobody really knows what's causing that. There's not a really strong argument that it's biological. In fact, methane on Mars is a very difficult thing to characterize altogether. It seems to come and go. It seems to be below the limits of detectability a lot of the time.
I guess there's no real reason why. I mean, if a planet like Mars does have some seasonality, look, chemical reactions are heat and potentially even just light based. Things could increase just simply because there is a season.
Exactly.
Doesn't mean that there's something lifey there.
There's a lot of false positives, really. But also with a lot of biosignatures, well, all of them, they still have false negatives as well.
So hang on, what's a false negative? That you don't see, is that where you don't see the methane, but it is there? Tell me.
Yeah, so misleading non-detection.
Right. Okay.
So if you think, we didn't see this particular thing, say methane on this particular planet, therefore there's no life there. Well, actually, maybe there's another process that's destroying the methane that's being produced by life.
Ah, I see. Yeah.
And so making that judgment may be premature.
Right. So just, I guess, not putting all your eggs in one particular astronomical basket, looking for multiple things, because you just never know how complicated the situation is on the planet you're looking at.
So having the most diverse range of biosignatures that we can put together that are readily able to be deployed, if you like, for a particular exoplanet, you'd want to have confirmation from 2 or 3 different methods, ideally, to be able to say, yes, all of these things are saying there's life, and they all agree. Yeah.
I mean, Mars, as you say, classic example that, well, we've seen, we think, this seasonal variation in this one thing. So therefore, life on Mars? No, not that simple. And that's Mars. Like, that's just the next one out. If you're looking at another planet around a completely different star a very long way away, then extraordinary claims require extraordinary evidence.
Indeed. You've got to get your 5 sigmas, which is a little bit of an in-joke.
Yes.
But basically...
got to be very, 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 very sure.
Yeah, very confident, basically, that you're measuring what you think you're measuring. So that's why I think this research fits into the biosignature puzzle in that way. It's kind of another tool that we can use to potentially say there is or is not life on an exoplanet. I did want to mention a few of the actual real difficulties that started to get my hopes down, if you like, by the end of this article.
You went into this paper going, fantastic, this is awesome. We'll have this knocked over by next year. No?
Yeah, well, it turns out that sometimes it's a bit more difficult than we actually thought. I mean, we thought it was difficult, but then it turns out to be even more tricky. So, I mean, our big new biosignature space telescope is the James Webb Space Telescope.
James Webb. And how long's James Webb been up there now?
-1 years.
Right. So due 2020.
I'm still going for a 2020 launch.
Oh, really?
Hopefully, maybe 2021.
Oh, come on, guys.
We'll
come on.
We'll see.
We're cheering for you.
Yeah. So JWST is going to be looking at some very basic biosignatures in spectroscopy. So it's going to be looking for atmospheres. And the way that we do that is by looking at transiting exoplanets. So these are ones passing in front of their host star, and some of that light from the host star is filtered through the atmosphere of the planet.
Yeah.
So we can look at changes that might be caused by the atmosphere of that planet.
Right. So you're no longer just looking at, hey, there's a planet there, because we saw the light from the star dip a little bit. You're now looking really, really carefully at that light and going, yeah, but how did it change?
Yeah.
What light got absorbed? What got transmitted?
So transmission spectroscopy is one of the biggest areas where we're kind of dumping research, if you like, into biosignatures. There's also reflection spectroscopy,
right,
which is where you wait for the planet to go just about before it goes behind the star. And at that point, it's reflecting a lot of light back at you from the atmosphere. So similarly, that light that's being reflected back at you will be changed a little bit by the atmosphere that it's bouncing off.
Great question. How do you, if you're looking at a planet which is just about to go behind the star, how do you see anything at all? Because you're looking basically at a star, which is really, really bright. So
remember, we're talking about like integrated light. So we're talking about the light of the planet plus star all the time. We can't separate for these close transits the light from the planet and star. It's just impossible. So we've got light from just star alone, say when the planet's in front of the star, or it's only got a little bit of atmosphere. And then we look at planet plus star just before it goes behind.
Right. So you've got your baseline of that's star, and then you've got planet plus star, and you just subtract one from the other.
Yep.
What's left?
Yeah. So those techniques are being really well developed. We have used them to say things like we have got some exoplanets with hydrogen atmospheres, helium in their atmospheres. So we have, and water and water vapor. So
this isn't hypothetical.
No, we can do very basic stuff, but we need to up the game quite a lot to be getting to the point of saying that these are biotic, these particular signatures. So the problem with JWST is that it's not actually going to be useful for this seasonal variation stuff.
How come?
Because you basically always got the same view of the planet.
How do you mean?
So if you think about seasons, then if you think about the emission spectroscopy, so when it's transiting, it's always got the same season pointing towards you.
Yeah.
So it's actually,
so you're not seeing seasons, you're just seeing
the same thing every year
over and over again. Hey, it's summer again. Oh, look, it's summer again.
So that's not super useful.
No.
So what we do really need is these to do imaging for these to get this seasonal variation. So we need very, very large aperture space telescopes.
Such as?
Well, mostly hypothetical.
Right. Okay. So when you say we need, what you're saying is, no, we need these.
Yeah, please build me some. There's a couple of projects being developed, but they're very, very early stages, and I didn't really want to go into the details because the chances of them being funded
let's not get
down the line.
Yeah. When you say large aperture, like are you like Hubble? Like that kind of aperture?
Oh, no, much bigger.
Right,
so like 10 meter.
Wow.
That sort of scale.
Hang on, what's Hubble?
Hubble was 1.8.
Okay, yeah. So you're talking really quite large.
Yeah. Big telescopes. Because we can do this
in
from
space.
This from the ground, whereby we've imaged exoplanets by basically sticking in a filter or a blocking circle that blocks out the light from the sun, and then you're able to the star, and then you're able to actually see the exoplanets going around. Problem is, most of these exoplanets are so far away from their host stars during those measurements that they're at least kind of Uranus's distance in our solar system.
Yeah.
Which also means they're going to take an awfully long time to go around their host planet.
Yeah, even seeing seasons at all is going to take you a while.
So it's going to take at least months, probably years, to gather these kinds of measurements. And the ones that are shorter than that, these planets on periods of days, are just too close for this blocking.
You can't just sort of stick your thumb in the way, metaphorically, and block out the star and just watch the planet going around, because they're just too close, and that would be too clumsy.
So I guess by the end of the paper, you sort of come into the point, well, yeah, this could really work, but we don't really have
on quite a long time scale with a lot of funding and building just the right kind of very large aperture telescopes in space.
Yeah.
Okay. Good. Right.
Crack on.
Right. Well, I don't know. Does that give us hope? It's really interesting, Emily. I love the idea that there's this, this very speculative side of what has become an incredibly specific and detailed part of modern astronomy, which is, hey, look, there's exoplanets. No, look, there's lots and lots of exoplanets. Let's measure the hell out of them. And then this paper comes along and says, well, look, here's a thing that we could do, but it's going to be really, really hard. I feel like what you're describing is sort of 10 years, like a decade plus of potential here. That is something that we could be looking at somewhat into the future, but it's not at all impossible.
Yeah, but you think back to astronomers in the 50s and 60s, they would have said exactly the same things about even detecting exoplanets.
Yeah.
They would have said, yeah, it's possible to do transits. Yeah, it's possible to do radial velocities of moving stars.
Yeah.
But we'll never, that's so far beyond the technological limits of the time. Yeah. Before we had silicon detectors even.
We'll never asterisk get there. And that asterisk gets you to, well, eventually there'll be a step change in the technology. Like gravitational waves. For 100 years it was never going to happen. You are off your tree if you think that we're going to be able to measure that. And then suddenly we can. And we've got a whole new kind of astronomy because the technology finally got there and suddenly we can do it. Well, here we are. We can't do it now, but 10 years, who knows?
Yeah, and I think astronomy is more ambitious than it's ever been before. When you look at some of the enormous global projects that we're building telescope arrays that expand basically the entire southern hemisphere with the SKA, the Square Kilometre Array, and radio dishes. We're building got real telescopes being built that are going to be between 10 and 20 meters in diameter. We're building lasers in space to measure gravitational waves.
Lasers in space. It doesn't get better than that.
Yeah.
So it's it's watch this space basically. Yeah. It's coming down the track, and this paper is saying, look, here's a really good thing to think about while you're waiting for the big space laser telescopes. That'd be awesome. Well, let's wrap this one up now. We are going to have to get out of here. So, if, like Keith, our wonderful patron, if you wanted to get in touch with us and send us a question, an idea, here's something that I've heard about on the news, here's a paper that I've just read, how could people get in touch with us, Emily? What would they do?
So they can tweet us if they've got a short enough paper.
Okay, yeah.
At SyzygyPod, SYZYGY pod. Hit us up on Facebook.
Yep.
Again, SyzygyPod. Yeah. We've got a beautiful website. I do love the website.
Syzygy.fm, yeah.
Every time I go, it just makes my heart go, oh, that's
very
us.
pretty. Yeah,
really
and there's a contact form on there, so you can just fill that one in and send it our way. We're on Instagram. We're on the Instas. We do. I kind of feel like we need to up our game on Insta, actually. Need to get a few more pictures out there.
Yeah.
If only astronomy had some nice images. I don't know. Gonna have to do some homework. And like Keith, if you wanted to support the show, there's a number of different ways that you could do that. First of all, you could just tell your friends and family, and we would love you to do that because there's so many people, as we found out in Thirsk last week, there's so many people who have no idea we even exist and yet go, astronomy, awesome, tell me more about that. So go and tell everyone you know, spread the word. Give us a review on Apple Podcasts, on Spotify, wherever you find your favorite podcast. Give us a review, give us some stars, help us float up through the noise. Or if you want to go that extra step, go to patreon.com/syzygypod. Go and find us there and sign up to become one of our wonderful, absolutely fabulous patrons, like Keith, who help to keep the lights on here at Syzygy Central, help us to do what we do, and help us to build this thing into the great astronomy podcast that we know it can be. So if you do that, we'll be forever thankful. And you can send us a little note like Keith did and say, hey, here's an idea. Have you thought about talking about this? We can have a bit of a chat about it and turn it into an entire show. You never know. Otherwise, we're going to have to wrap it up from there, I think. So, Emily, we'll be back in about a week or so. I'm watching the board behind you fill up with lots of different ideas. We're not going to run out of stuff to talk about.
It feels like it's publishing season at the moment. I mean, there's just stuff coming out every day. It's really exciting.
There was a bit of a pause there after summer when everyone went, oh, okay, what are we doing? And then suddenly there's just astronomy stuff everywhere. So we'll be back in about a week or so with another episode of your favorite astronomy podcast. Until then, see you later.
See you later.
Bye, everybody.